going through all this circuit. My point is here, phi m and phi g, they are equal. Phi m is equal to phi g, and let's call it phi. It's like it's current in a series circuit. You know, current all the way is the same. Doesn't matter how much is the resistance of this one, how much is the resistance of this one. Current is the same when they are series. Now let's replace them here again. So Hm is going to be phi over mu Am, and Hg is going to be phi over mu 0 Ag. Now let's replace this one in the above equation over there. We'll go all this through. So Hm is going to be phi over mu Am times Lm plus Hg is going to be phi over mu 0 Ag times Lg equal to Ni. Let's put it here. It's going to be Lm over mu Am plus Lg over mu 0 Ag times phi is equal to Ni. Right? Now just to remind you, what was the definition of the reluctance? Reluctance was L over mu A, right? So what is this? Lm over mu Am. This one is Lg over mu 0 Ag, right? Basically, this is the magnetic reluctance of the core. This one is the reluctance of the gap, right? We have one for this part and one for this part, right? So basically, it's going to be Rm plus Rg times phi is equal to Ni. We went through this one just only for this time. Now we went to do the proof to show you how it does work. Now if I'm going to draw a circuit to show that equation, how it's going to be, I'm going to have a source, right, like before. As soon as we have the winding, we are going to put a voltage source for that, right? It's going to be a voltage source of how much? Ni. And look at here, the flux is going this way, right? So the positive should be here. This is a positive, and this is a negative, and this is a flux. The next one, we are going to have one magnetic resistance for the core, one magnetic resistance for the air gap. So it's going to be like this. This is circuit, equivalent circuit of this. So basically, when we have two materials, you put two resistors. Now, I want to talk about one more thing. Why I called here Ag? Because I want to talk about that one. See, flux. Look at here. Flux everywhere is the same. Is the H the same or not? H. Is it going to be H the same for all of them? No. Why? Permeability is different, exactly. For the magnetic part, permeability is something, and for the non-magnetic parts is something else. That's the main reason, because they have different mu, right? But now let's talk about B. To get into the B, see, I call this one Ag. I'm gonna zoom in here. I'm gonna zoom in here how it is. No, so just look at it this way. This is this part. This part I'm wrong. Ideally, if you look at the flux is gonna be like this. It's gonna go all the way down. Perfectly like this. So if it's like this, look at here. This is a what cross section? This is a AM, right? It's coming through here. What cross section is this one? AG. If it's like this, it goes straight down. AM and AG, they are the same, right? No difference. But in reality, it's not going to be like this. In reality, it's going to be like this. When the flux is coming down, it's going to open up. Then it's going to go to the air. If you do finite element, you can see, if you, nowadays it's easy. If even you go type in Google, you say fringing flux in the air gap, bring you some pictures of those when you can see the finite element result if you are interested to see. See this one now is the AG, right? This one is the AM, right? The flux is going to open. They call it fringing flux. They call it fringing flux. Flux is going to open up. In reality, it's going to be like this. Usually they say, let's say, I'm going to give this one a little bit dimension here. Let's say this one is A, and this one is B, for example. This is a cross section of this core. So AM basically is A times B, right? AM is A times B. But AG, they say, for example, A plus X times B plus X. X is a fringing effect, 5%, 10%, something like that. If you want to consider the fringing effect. You don't know how much is the X, but we can go, for example, either in the problem we tell you, hey, consider 5%, fringing, or I don't know, 10%, or if we will not say anything, just assume it's ideal. AG and AM, they are the same. AG and AM, they are the same. Yes. Definitely it does. The bigger the gap, the fringing is worse. The fringing is worse. See, this one, I don't want to get to the very much of detail. But this thing is going to cause a lot of magnetic loss. About the eddy current and hysteresis loss we talked. This one is one of the big things. When I was in GM, we were working on a project. They call it fuel cell car. Fuel cell car, they have these DC to DC converters, and all converters, they need an inductor in the circuit. So we designed the inductor. Just I want to let you know how much this one is. It doesn't look like that much important. I can bring it one day to show you all the finite element analysis we did. The core we used, it was a C core. C core is like that. They call it C core, that one. So we had something like this, 2 C core. That was one design. I'll bring it to show you guys. Let's see. 3 months, heavy finite element calculation to get to this thing. Just 1 second. This one was the core we had, and we calculated the loss. There was a copper loss because you have a winding, and there is a magnetic loss. So we calculated for this one. If I'm calling it correctly, the total was 260 watt. 260 watt. We had total. It's very huge loss. There is a switching loss. You learn those one in power electronics. When you have converter, you have a switching loss and you have a magnetic loss. So to be honest, what we did, we look at the Lexus hybrid. Toyota is perfect. For a piece of art. If you look at their power electronics work, it's a piece of art. I'm talking about 2006-07. What they did? They came up with this idea. And I modeled all these things. It's the one gap, for example, this gap, for example, let's say was 3 millimeter. They came up with 1, 1, and 1. 3, 1, they call it distributed gap. They distributed the gap. So if you look at here, for example, the flux is going to go like this, because it's a big gap. If you look at here, the flux is still going to go, but it's a little bit of fringing. This one, the loss dropped to 161. 101. See, 101 is about 40% of the loss gone. I'll bring those numbers to show you. I had that one. If I had my computer, I can show you. to see this number. I'm not sure exactly what they are, but I'll bring it and you can see. This one was the best design to have. But the problem with this one, can you tell me what's the problem with this design? What?
A lot of pieces.
A lot of pieces. So what's the problem with lots of pieces?
How you put them together.
How to put it together? Manufacturing. Manufacturing was a big problem for this one to build this one. But this one was the best design. Just I want to tell you, now they asked, if this one depends to the air gap? Yes, depends to the air gap. And the reason this is important, maybe you ask, why this one is affecting the loss? Look at here, if you are completely straight, you don't have a dc over dt. The lines are good, but as soon as you start to bend like this, there's a dc over dt. dc over dt is going to end up with a loss. It's going to translate to loss. Let me shut down this. So, but just to make it very simple, this one was kind of a story to know why these air gaps are important. You have to, many times you have to add air gap to the system to prevent saturation. If you compare these two numbers, usually Rg is very bigger than Rn. So if you go back to the BH curve, I talked about the BH curve. Remember BH curve is not like this. This is the B versus H, right? So you don't want to come here. You don't want to come here because saturation is going to cause lots of problems. You know, heating, not working linearly, all those kind of things. To prevent getting there, you have to stay here. You have to control your B. To control the B, you have to have this one is usually small. You have to have a resistor here to control the flux, right? See, look at here, flux. Flux is Ni over Rm plus Rg, right? You design your circuit. You say, hey, I want to work with 1 Tesla, for example, 1.2 Tesla. This is 1.2 Tesla, for example, is going to be here. This is the part of design, you know. So I want to be here, right? You say 1.2 Tesla, let's go backward. How much resistance do I want to in my circuit? So you go and you say, okay, I select this type of core. So this type of core is going to give me this much resistance. Still, I'm short this much. So I'm going to go add a gap, millimeter, half a millimeter, 2 millimeter, whatever. You know, you calculate those things to make your circuit to work. You know, on that point you select it. You think you have the best performance for the circuit. So adding air gap, you can control the flux in the circuit. Control, I mean you design it. It's not like that. Every time you can change the air gap. No, you design it once, and that one is going to keep the flux where it should be. So this is the story with the air gap. And now, let me see what's next. Let's go through one simple example. I'll go toward the example toward the end of the class. Let's leave the example for a little bit later. Now, inductance calculation. You guys are a little bit familiar with inductance calculation because we use it in the power system course. If one of you remind me about this example, I'll bring it Tuesday. You know, just let me know in the discussion session. I'll bring this one. All of you have seen inductors, right? This inductor, mostly they are something like this. There is a piece of core with some winding on it is an inductance, right? But have you ever thought about it if you want to, hey, I want a 1 millihenry inductance or 2 millihenry inductance, you want to a specific value. So how should I design this inductor to get to that number? So we'll talk about it to see what parameters are important for designing an inductor. Before moving to this part, I said air gap is the way, you know, usually you control the flux. Now new materials, they are like a donut usually. Most of them, they are like a donut. There are two types of core. They are like an EI core. You have seen it in the regular transformers. And they have a donut cores usually. There is no air gap. What they do with those ones, they are like a donut. Each of them has a different, you know, characteristic. But usually they mix the magnetic material with some non-magnetic material, like a glass, something like that, like a silicon. And kind of, think about it. This is a kind of central here. They distributed this one all over. You know what I'm saying? Mixing it with something non-magnetic, basically is reducing the magnetic capability of the core a little bit. But it's completely uniformly distributed on the core. This one is just central, it's just here. But those ones, you see the full donuts, they have added some silicon, some percentage of silicon to reduce, to basically increase the R. Look at here. If you look at the R, mu is here is the number. When you add more glass for air, we know is a 4 pi times 10 to the power of -7. For example, a magnetic material, I don't know, is for example 5,000 times of this one. But when you add, for example, glass to that magnetic material, this one, for example, from 5,000 is going to drop to 4,000 or 3,000, based on how much you are adding to that, to mix it, you know what I'm saying? Kind of, the advantage of that was there is no fringing flux. That's the best thing, There isn't, I talked over there about the distributed air gap, right? If you kind of mix it, the air gap is all over here. You know what I'm saying? It's distributed all over this path.
What's the loss?
Loss is better, but the cost is more. When you make those cores, you know what I'm saying? The cost of those cores are more than this regular one.
In this case, that's an air gap, right? Why don't they just use a different material to fill in that gap?
Is not usually air. It's like plastic, because when you have these things, you don't leave it like air, because of mechanical things. Usually put a piece of plastic here, but plastic is like air. Usually you don't leave it open. Even that one I mentioned over there. Think about it. This one is an inductor inside the car. It cannot be air between these two. You put a kind of piece of material is the same permeability as air, like a plastic. Because you have to still, what we do, we put a tie wrap, not tie wrap something, we put a tie wrap around this one to hold this one together. You don't want them to move. If they move, it's going to change the inductance, right? So you have to keep the air gap, so you put a kind of material like a plastic, something like that. You need, based on the application you have, to keep them together. You can squeeze them together and keep it. But here, for simplicity, I'm saying just the gap.
Have they ever tried a different material and see if it has the losses?
Yeah, definitely. They have tried different materials,
So which one's the best?
I don't know. They did the application. Which car is the best car? No, I'm going to say, simulate your question. Which car is the best car?
Depends on application.
Depends your pocket. If you have if you have, for example, $15,000, maybe. I'm not saying I'm not advertising for any car company. Maybe, for example, Ford Echo something is the best car for you. If you are a billionaire, yeah, maybe, I don't know, we go for, you don't care about the money, all performance. This is exactly here, I'm saying which material is the best. Once you want to design a kind of missile, so cost doesn't matter, You're going to go, once you are going to design a cheap, charger for your cell phone or something, yeah, that's you go select the cheapest material you can, because you don't care about that much of performance, This is dependent where you're going to use it. Inductance. Before going to inductance, let's kind of remind you what was the Faraday's law. Faraday's law, it said E in the induced voltage is equal to N dphi over dt. This is for, let me put the circuit here. This is like exactly transformer we had in the previous course. For example, you have a somehow you have flux in this circuit. Somehow, how you can have flux here? If you have another winding here, right? Like a transformer. Connect this one to a source, right? It's going to generate flux here, right? When it generates flux, this one is going to generate voltage here, right? How much is this voltage? E. And this is an N. You can use the Faraday's law to calculate this